students, and welcome to this lesson where we're going to talk about the transformations of parent functions. I encourage you to watch the first graphs of parent functions video prior to watching this video because I'm going to work under the expectation that you already feel comfortable with the equations of your parent functions. To just quickly refresh your memory, there are 6 parent functions. They are the linear function, the quadratic function, the cubic function, the square root function, the absolute value function, and the rational function. And you have learned for each of those functions that there is an equation that is related to the bare minimum original parent function. So the purpose of this video is to think about equations that fit underneath one of those parent functions, but there have been some types of transformations done to them. When I use that word transformation, I mean that the graph looks a little different. Maybe it's been moved up, down, right, left. Maybe it's been, expanded so it looks larger or smaller. And so these are the types of things that we're going to talk about. The very first type of transformation I want you to feel comfortable with is something called a rigid transformation. When I think about a rigid transformation, I am referring to something where the shape does not change. So there is some type of movement, but the shape of that object does not change. So I want you to imagine you are at a table and you place an item on that table. Let's put a flower vase on the middle of the table. And let's say I begin to move that flower vase around. I move it up or I move it down, or maybe I move it to the left or to the right. I'm moving it in all the different places of my table. No matter how I move that, the vase is not changing its shape. It's just changing its particular location. And so that is what we refer to as a rigid transformation. So anything that moves up, down, right, or left, as well as reflections, because a reflection doesn't really change its shape either, right? You're just flipping it across, we call it a line of symmetry. So we're, our line of reflection. And so we're flipping it across. So again, it's changing location, but its actual shape is not changing. So we're going to think about a function, and we're going to write all of our different transformations kind of in a broad context. But while I'm writing that, I'm going to actually use an exact example, and I'll pick y equals x squared just to kind of help you think through. So y equals x squared is the quadratic function. When I say y equals f of x, I'm saying I can be talking about any of my parent functions that I want to talk about. So if I am going to move up, I am going to take whatever the function is, so whatever parent function, and I am going to add some number. By adding some number, that lets me know that I would like to move my function up. So if I was dealing with the quadratic function, I would say, all right, I have the parent function of a quadratic, but maybe I want to move it up 3 units. I would do plus 3. And the way I'm going to start explaining stuff is saying it's in the inside or the outside of the function. So what I mean by that is here's the parent function, x squared, and plus 3 is on the outside because it's occurring after I've written out the entire parent function. Okay? All right. My next direction would be going down. So you probably can assume what that will look like. Y equals f of x minus a number. So if I want to go down, I'm going to subtract a value on the outside of the parent function. So if I had x squared and I wanted to go down 5 units, I would say down 5 units. Again, here's the parent function, and minus 5 is outside or occurring after I've written the entire function. The next direction would be right. This one's going to seem a little weird. We've already written 2 up and down. We've written 2 different types of transformations where I add or subtract on the outside of the parent function. So now when I go right and when I go left, I'm going to have to work within the parent function. So that's going to look like f of x, and then I'm going to leave a space for the operation and a number inside the parentheses. So you'll notice the format is the same for both of these. But a lot of us would probably think that right would be positive and left would be negative. It's actually the opposite sign of what you would think. The reason why I say we would think that is because when I go and I look at a Cartesian graph or a Cartesian plane and I move to the right, that's going to the positive direction. But if I am trying to show algebraically that I've moved to the right, I actually subtract a number. Whereas if I want to algebraically show that I've moved to the left, I'm going to add a number. So again, this is occurring within the function, so I can't just add or subtract after I've written the function. What makes the parent function in this particular example is that I have x and squared, right? So that squared is the thing that's really defining the type of parent function I had. Because if that number 2 wasn't there, then I would have just x, and that would be a linear function, right? But it's the 2 that tells me this is quadratic. If it was a 3, that would be telling me it was cubic. And so let's say I want to move right 2 units. Well, I'm going to subtract 2 on the inside of that parentheses. If I wanted to move to the left, again, x squared's the parent function. If I want to move to the left maybe 3 units, I would add 3 on the inside of the function. Okay? All right, so those are how we move up, down, right, left. Again, keep in mind that, right and left is the opposite of what you would think it is, and you are either adding or subtracting your number on the inside of the function rather than the outside, as we would kind of assume. So if you've noticed the way that I was doing the example, I was telling you, we have the quadratic parent function, we want to move up 3. And so I was giving you the descriptive terms, and then you were writing the algebra for that. That is one way that you could see questions be asked of you on a test. However, another way is for me to tell you, okay, you have the parent function, f of x is equal to x cubed. This is an example. So you would need to know that that is your cubic function. And then I would tell you, okay, here's one transformation. So x to the third minus 1. Here's a second transformation, x minus 1 to the third. And here's a third transformation, x plus 2 all to the third plus 1. Now you tell me the transformations that have occurred. So on problem number 1, I see the parent function x cubed, and after it I see minus 1. So that corresponds to going down 1 unit. It's very important that you're telling me the direction, which is down, and how many, which is 1 unit. Looking at the second example, I see a minus 1, but it is on the inside of the parent function. So minus on the inside means that I went right 1 unit. And looking at number 3, I actually see a couple of things here. So the first thing I notice is I have a plus 2 on the inside of that parent function because it's within the x to the third. So a plus lets me know I moved left 2 units. But then I also see a positive 1 that's occurring after the parent function. And that corresponds to going up 1 unit. Another type of rigid transformation that we can have is something called a reflection. It is basically the mirror transformation. So you have some point or some line, I call it a fence of reflection that you reflect across. And for the purposes of transforming with parent functions, we are going to either reflect, so let me write the word reflections. And we are going to talk about either reflecting across the x-axis or reflecting across the y-axis. So when you're working with reflections, with transformations, you're going to identify that there's been a reflection and where, which would be x-axis or y-axis. Now, this doesn't mean those are the only lines or the only things that you're able to reflect over. That's just what we're going to be working on. So if you just think about it for a second, if I draw a quick little coordinate plane here, and I'm going to be a little lazy, so forgive me, but I'm going to just make it a dot, okay? If I wanted to reflect across my y-axis, here is my y-axis. Because this point is only 1 unit horizontally from the y-axis, it needs to be 1 unit on the other side as well. So this would be my reflection point. If I wanted to reflect across my x-axis, because this point is 2 units above my x-axis, I need to be 2 units below my x-axis when I create its reflection point. So you just want to make sure you're thinking about, if I reflect on the y-axis, I'm moving in a horizontal direction, right? I went from the left side of my screen, this side, to the right-hand side of my screen. That was when I was reflecting across the y-axis. But when I reflected from my x-axis, I started up above my x-axis and I ended up down or below my x-axis. So x-axis moves things in a vertical direction and y-axis moves things in a horizontal direction. The reason why I say that is because we represent reflections with a negative sign. If I am representing an x-axis reflection, I have my function, so y is equal to f of x, and I am going to put a negative in the front of that parent function. Whereas if I'm reflecting across the y-axis, I am going to put my negative inside of my parent function. And I find this helpful because I actually want to relate it to moving up, down, left, right. When I move up to down, like if I'm moving up a certain number of units or down a certain number of units, we put the plus or minus sign on the outside of the parent function. Likewise, when I'm reflecting across my x-axis, I'm moving in an up-down direction, I put the multiplying of a negative on the outside of the parent function. Whereas with a y-axis, I'm moving in a left to right direction, just like when I want to move left a certain number of units or right a certain number of units. When I want to reflect across the y-axis, I'm going to multiply my negative on the inside of the parent function. So there's this relationship between vertical type movements versus horizontal movements and the placement of the plus or minus, operation, whether that's multiplying by a negative or adding or subtracting a certain number of units. Okay, so just to give you an example before we move forward, let's say I was working with the function y is equal to, let's do, I'm trying to think of something that I think will, really help you make sure you understand. Like, let's do x to the third power, cubic. If I want to represent a reflection across the x-axis, then there's already x to the third, right? And I'm going to put a negative outside of that. So this is saying negative times x times x times x. Whereas if I wanted to represent a y-axis transformation, or reflection across the y-axis transformation, I would do my x to the third, but I would put the negative inside of parentheses because I want to show that the negative is being cubed as well, because this is saying negative x times negative x times negative x. And so that's kind of the difference on why it matters, where I put that negative. Generally, it's helpful to use parentheses. So if it helps you understand like x to the third and then the negative is outside and using those parentheses helps you to visualize that better, then you're more than welcome to do so. Okay. As always, I hope that this video was helpful for you to understand rigid transformations. If you have questions or concerns, please don't hesitate to reach out.